This is probably the most exciting lecture I can think of, especially because I don't have to follow a slideshow. So what we're going to talk about is essentially nonlinearities. Or actually, I should talk a bit. I know it was a long time ago, but the last lectorial you had with me had some exercises that you guys have been doing. So I just take a bit of time and see if we can remember to reflect on this, because it's a good practice. So one of the really interesting things was what I've heard from the groups is that the groups that took a high quality hardware device were totally bored to death. And people who took these cheapo things were really excited about discovering in how many possible ways things can be wrong. So I remember one of the filters on one of these mixers just didn't have anything looking like a cutoff frequency at the claimed number of kilohertz. Which group was that? Maybe some of you here. And it actually did a dip before the peak as well. So it didn't just do a, increasing the gain at a certain spectral in a certain range. It did things all over the place. And then I think crosstalk was also discovered as a big thing. But maybe I'll remember more if I look at this. So what we looked at is EQ settings and identifying the baseline of accuracy. So what is this baseline of accuracy? Well, what am I trying to... I mean, I've been talking about it, but I've left it deliberately a bit more vague for the last bit. So it is important to remember that, it's not ideal scenario for measurement, what we have. In fact, what we do is we estimate things. So it's good to see what is, so to speak, the tolerance, actually, that we have to assume in terms of reading results. Okay, so what we've done and what we've seen is that we can do this kind of baseline measurement, figure out what is, what's gonna go wrong or what may go wrong without anything else being a factor. What we've done is we've performed the same measurement twice, 2 minutes apart. Okay, and then we've looked at the differences between those measurements, and what has transpired is that in larger, more reverberant rooms, even up to 150 hertz, you would get largely different measurement results for the same position of microphone and speaker. Okay. In smaller rooms, this was a bit more controlled. So it seemed like 70, 60 hertz, it was still kind of reliable. If you keep repeating the same measurement, you keep getting the same results. That's what we're looking at here. But even in the small, more controlled rooms, what we found is that, 50 hertz, I'm just not sure how reliable that may ever be, because if I take two measurements at the same condition and I get two different results, it just says that something is wrong here. And similarly at the top end, at some point things just seem to become inconsistent from one measurement to the other. Okay, so obviously in a hardware device we expect less of an issue, right? We do expect that the measurements will be consistent, more consistent than in the space. So that's what I hinted at there. Kind of do the same measurement twice, look at the difference between those and make your conclusions. So in REW we are doing this by dividing the spectra. And then we can see a single graph that tells us, okay, what is the baseline? What is it that we can assume? And on top of that, it's not just a threshold, like, okay, everything below 150 hertz is trash, but we can actually express that continuously, right? So we can actually say that the tolerance increases below 150 hertz, and at 100 hertz it's about 6 dB, at 50 hertz it's already 20 dB, whatever it is. So we can actually quantify that quite neatly as well. Okay, and then what you guys have been doing is essentially looking at the EQ graphs but measured EQ graphs. And that was quite exciting. You guys remember anything interesting arising from that? The thing was to try and produce a single graph that says it all. Okay, so this was one of the messages and also for your final year project, it's still very frequent that we get someone who just appendicizes 20, 30 graphs and says, well, there it is. Okay, so please try to avoid this. A good graph is the graph that you actually spend time looking at, and as you do that, you discover facts, you discover things about the graph, and obviously if this is part of your thesis, then it's expected that we can read it as well. Okay, so what do you see in this graph? How do you interpret certain things? So that was the attempt here to actually get 5 curves looking at these essentially spectral responses based on different EQ settings. So I believe some groups had a fairly neatly spaced set of lines. And in other groups, I seem to remember that there was a bit of a mumbo jumbo all over the place. Obviously, it's not quite easy to dial in the exact same distance, so to speak, from a certain setting. But I think it was I was surprised as well. Some of these mixers just do EQing all over the place. Okay, then this was the catch of the show last time, the punchline. So what I'm saying is that the cutoff point of a filter is said to be the frequency at which it cuts 3 dB. Okay, so then I asked you to take a filter band, measure the transfer at an extreme, medium, and gentle attenuation setting, and pinpoint and discuss the cutoff points for these 3 settings. Okay, so the thing there is that if you go by the rule of 3 dB is the cutoff point, then actually depending on the amount of attenuation, you will get a different cutoff point, right? Whereas technically speaking, the condensers and the coils, although it's probably some kind of op-amp circuit anyway, they will not change the cutoff frequency. It's just how are you reading it that changes. So that was there to kind of alert you to, stay skeptical about stuff that you read. And then actually the second punchline was that there is also a distinction between shelving filters and what you may call resonant filters. Okay, so even if a filter does not display a resonance peak, right? If it's a first order 6 dB filter, if it's not a shelving filter, it's actually a resonant filter. Okay, it has this cutoff point. Okay, so that would have been the second punchline. Think about that. Maybe there is no cutoff point to discuss. And in fact, if it is a bandpass filter, then we call it the center frequency and not the cutoff frequency as well. So there was a few things to discover kind of hidden in there. And I think we've discussed this with the relevant groups at the time. Okay, and then finally we looked at DC coupled hardware. And the message there is that a DC coupled device will actually translate a fixed voltage. So if you put a fixed voltage at the input, you will get a fixed voltage at the output, and obviously depending on the amplifying factor. So this means for speakers which are DC coupled throughout, so typically the amplifier and the crossover or whichever other component is there, is that if you put a battery, you can actually try this at home, it's pretty safe. You can put a 1.5 volt battery on the terminals of the speaker, and if you see that the membrane has moved in or out and stayed there, you know it's a DC coupled system. But if the membrane just jerks out and goes back to equilibrium, then it means that it's not DC coupled. So DC is an interesting term. Obviously stands for direct current. But what it is, the interesting bit is that it's actually 0 hertz energy. And well, maybe it's a good time to get a bit into this because we're talking about filters, and no one else is going to tell you anyway, ever again. I'll try not to get emotional. But the FFT, as a spectral analysis procedure, does not use filtering. Yeah? So you see, it's a kind of a thing, because initially when you start to get into spectral analysis, you're like, okay, well, I'm interested in what happens at 500 hertz, so I'm probably filtering the rest out in order to find out what's happening there. But actually, no. That would be a filter bank. So you could have a filter bank-based spectral analyzer, and the old analog gear was filter bank-based spectral analysis. Now, the FFT, what it does a sideband trick. And that's what I'm actually taking some time to talk about it, because I'm going to talk about sidebands today anyway. And it actually has this 0 DC, 0 hertz trick as well. So what happens, I guess I used to teach synthesis and I was hammering on this quite a bit, but I imagine you guys never really been, questioned what happens if I multiply a sine wave by itself. I mean, multiplication to start with should, I guess, be clear. If some of you are doing Max MSP or some other kind of programming audio stuff, you understand that multiplying a signal with a fixed value will change the gain, right? Now, multiplying a signal with a sine wave is actually your ring modulator, okay? So what happens is that if you multiply two sine waves, you get sidebands. And these sidebands are the sum and the difference frequencies of those two sine waves. Okay? So that's your sidebands. And the interesting thing here, the relevant thing here is that if you multiply the sine wave with itself, in other words, if you square the sine wave, then you get two sidebands. One is double that frequency, because it's the same frequency, and the other one is 0 hertz frequency, because it's one minus the other. So actually, if you square a sine wave, what you get is a sine wave at twice the frequency and a DC offset. So you actually get a clean sine wave, but not at the original frequency. The original frequency energy is gone. There is nothing if I multiply 100 hertz sine wave with a 100 hertz sine wave, and the result, there is no 100 hertz left. There is only 200 hertz and 0 hertz. And this is the phenomenon that actually supports Fourier transform. So actually, fast Fourier transform gets a bit more complex, because it's a kind of a tree structure algorithm. I won't go into this. But your original Fourier transform, the original spectral analysis, which, by the way, came from heat waves in metals in the 17th century, totally out of context. But what happens is that you take an audio signal, you make sure there is no 0 hertz energy, that there is no DC component, you multiply it with a 100 hertz sine wave, and the amount of DC offset you get at the end is the amount of 100 hertz energy that there was at the start. So you don't filter out things, you just use this phenomenon of getting DC offset from squaring a sine wave. So essentially you square only the 100 hertz component in the original signal, and the level of that component is proportional to the DC offset once you've done the multiplication. So that's this really neat DC kind of trick that goes into Fourier transform, and which also says something about the sidebands. So actually I'm gonna get straight to business here in terms of these sidebands. I mean, first of all, just a gentle introduction. So I've actually introduced nonlinear distortions, and the main message is you get new spectral components, okay? With nonlinear processes, things that weren't there suddenly exist. With filtering and linear processes, you are shaping the existing spectral components, but there may be no new spectral components whatsoever. Okay, so that's this, in terms of signal processing understanding, that's a huge dividing fact between linear processes and non-linear processes. So what you then get is, if you put a sine wave into the system, you get that sine wave plus its harmonics. Okay, that's essentially what harmonic distortion is. And if you do look at the distortion graph, which is derived from impulse response, or actually from the sine sweep, I should be more precise, in REW, you get to see this picture. So this is my distortion tab here. And what I have then is first the level of the fundamental, which is my spectral response. And then I have the level of each harmonic right there. So what I see then is how much of second harmonic I get for each of the spectral bands that I'm looking at, right? So the point is that you can read this graph. Let's try to read this graph at 100 hertz, okay? So it says that when the system outputs 98 dB of 100 hertz signal, then the second harmonic is at 72 dB. Okay? So you can actually read out the amount, the level of the second harmonic at a given frequency. And actually, if you subtracted these graphs, then you can see the amount of harmonic distortion independent of the actual spectral response, right? So you see, for example, at this frequency, whatever that is, I have a dip, let's call it 1.8 kilohertz, and then the second harmonic there is at the level of 42 dB, right? But actually, this is a huge amount of harmonic distortion because the amount is actually the difference between these two graphs. Okay, so this holds then for all the harmonics as you see them, and typically they drop in level. Okay, typically they can trace a similar shape. So if you have, for example, you see here I have these peaks kind of bundling up, so there is an issue with the system there, right? Now the thing that you might remember me saying is that looking at this graph can also give you a hint whether the measurement was incorrect or flawed for any possible reason, because if there is a huge anomaly, if there is, you know, a door being slammed while the sine sweep was running, then at that frequency I would read a lot of harmonic distortion, right? So what you can say then is that the measurement of harmonic distortion is even more sensitive to external disturbances, because actually every external disturbance will be part of the graph. Okay? Now, in terms of the harmonics of a signal, the interesting thing is that psychoacoustically we don't tend to hear out separate signals in a scenario when you distort a sine wave, right? So if I take a sine wave and I start distorting it, what I hear typically is that it gets a bit more sharp, a bit more piercing, or a bit more rich, depending on the frequency itself. But essentially, it's really important to note that having an increased amount of harmonics generated by the system may actually sound good and better. Okay? I mean, if you are trying to make music that sounds forceful, loud, you know, present and strong, you actually depend on harmonic distortion quite a lot, right? If you have a very excellent linear speaker, it's much more difficult to get it to sound like it's really doing it, right? So actually, you know, suboptimal speakers can do great service to providing that sound of aggressive, forceful, you name it, which is quite obvious because that's where distortion first arose in our understanding of things, which is, you know, small guitar amplifiers being whacked up and then people realizing, oh, well, that's a really interesting sound, right? Because initially it was like, well, don't use the amplifier in the nonlinear range because it's not amplifying the guitar, it's giving you a lot of rubbish. But actually that rubbish has gained a huge appreciation in terms of its musical characteristics. So actually the thing with harmonics is fairly straightforward. I kind of expect you guys, you know, knowing most of this already anyway. There is a measure of total harmonic distortion, which is kind of all these harmonics added up. This should actually be a good, you know, kind of flash, hopefully, that next time you see a THD expressed with a number rather than a graph, that you do feel a bit underwhelmed by the engineers who have done that, because now you see an actual THD graph and you see that the amount of harmonic distortion varies greatly in different spectral regions. And if you want to know more about the system, that's what you need. And if you just express it with a single number at 1 kilohertz, it's kind of underwhelming. Okay, so that's the harmonic distortion. That's straightforward. The really exciting thing is the intermodulation distortion. Okay, so this is this next chapter, and the intermodulation distortion has a link to sidebands. That's why I started talking a bit about sidebands. And you may know that AM synths produce sidebands, right? Ring modulation produces sidebands. In fact, frequency modulation is also a sideband producing synthesis algorithm. The difference is that the FM will produce higher order sidebands as well, whereas amplitude modulation, ring modulation will produce only only first order sidebands. So first order sidebands are A plus B and A minus B, right? So you get a sideband essentially when two sine waves interfere. And if there is a nonlinearity involved. Okay, so technically if I just play two sine waves in this space, you don't really expect to find energy at the sidebands, but you actually might. And the reason you might is because of the speakers. So that's actually a really interesting experiment. Maybe that could have been the second thing that these days is, you know, just come up with an experiment. You see, you can do this, try it, it's very exciting. If you play two sine waves from a single speaker, see whether you have intermodulation components, and then play those two sine waves from two separate speakers. And my suggestion is that if you play it from two separate speakers, you will see far less, if any, intermodulation components. Okay, so to make this a bit more understandable, hopefully, what I can do then is actually play two sine waves. Okay, so that's the point. You see, if I'm just looking at harmonic distortion, one sine wave is plenty. Deal done. If I want to see anything about intermodulation distortion components, I need two sine waves. I will never discover it from looking at a single sine wave. Okay? Hint, that's why there is no intermodulation graph in the distortion plot, because it was measured with a single sine wave, right? So to measure intermodulation distortion, you need two sine waves. And they need to be of a different frequency. And as I said, what you get then is you look at the sum frequency and the difference frequency. So here are some standard sine wave pairings. So SMPTE is obviously problematic because some of the systems that we're looking at, if it's speakers, typically have issues at 60 Hertz already, right? So for speakers, we very frequently use the DIN, where we have the 250 and the 8 kilohertz. So if I play these two sine waves through a speaker, there will be harmonic distortion. So for 250 hertz, right, I will get twice that frequency 3 times and so forth, all dropping in level. I will get the same for 8 kilohertz. But the interesting thing is that I will also get a frequency of 7,750 hertz. I mean 7,750 hertz. Okay, so that will be 8 kilohertz minus 250. I will also get a spectral component at 8,250 hertz. And that's what happens. So those are your intermodulation components. So I can actually see them live as well. So I will play this. And then I can do a real-time analysis window. Okay. And the point is that if I am in a linear region without much distortion, in fact, if I'm in a totally linear region, then there will be no sidebands. Now, obviously, here my speaking voice is recorded as well. So you see, now can I freeze that? Okay, so you see at this stage, I'm seeing the two frequencies. I see the 250 hertz and I see the 8 kilohertz and not much else. Some kind of rumble is coming through as well. Okay, now the point is that if I increase the volume, then those are your sidebands. Okay, sorry, I should say intermodulation components. So you see, the math is the same. A plus B, A minus B. Some frequency, different frequencies. The same math for sidebands, which is the term when we use discussing sound synthesis, just as it is the same math for the distortion when we call it intermodulation components. By the way, there are, I think Pauline Oliveros at some point made pieces with for accordion, which were actually trying to make people realize that there are such things as different tones. So in accordions, if you have kind of really pure sounds, you can actually hear out these frequencies. So back to the psychoacoustics, you see, if I have only harmonics added to the signal, it is rather unlikely that I will hear an addition. I will hear a transformation. Okay, so the timbre changes. You see, if I have a 100 hertz sine wave and I play 800 hertz sine wave next to it and much softer, I will not hear the 800 hertz sine wave as a different signal. I will hear the 100 hertz signal change timbre. Okay, so that's a bit of psychoacoustics that we didn't really get into much, but there's a few things, few characteristics that really merge well into a timbre, sensation of timbre. So one of them is the harmonics, but the other one is also common fate. All right, so this kind of links back to Gestalt principles that you might have encountered previously. So I can actually also make an 803 hertz sine wave become part of the timbre of a 100 hertz sine wave if they have common fate, which means that if I apply the same amplitude envelope to them, or same amplitude modulation or pitch modulation. So if you have a mixture of sine waves which are not harmonically related, but they jump up and down together, so to speak, again, it is likely that you will hear them as a single sound source. Okay, so it's actually really important, I think, also for, you know, kind of making snare sounds, you know, and hi-hat sounds. You know, a lot of the early work that we do, you know, getting there, typically has one hi-hat sound or one snare sound, but actually layering these things with great attention to detail is what gives you a very rich timbre. And it won't give you necessarily two sound sources. but it will allow you to have a more rich sound source. So this kind of ability, or I should say it's unfortunately you can't even switch it off, right? So you could. I won't go into that. But the thing is that, you see, our recognition of sound sources is a very complex neurological phenomenon. The fact that we essentially group together a lot of neural activity into the percept of a single sound source is a really big deal. Okay? So what happens actually, I mean, if you read a more simplistic account of this, then you would get a story along the lines, yes, well, the ear separates the frequencies and then the brainstem unites them back again. I'm not a great fan of this kind of trivialization of what's going on, especially because later in the physiology, neurology of hearing, it became really apparent that there is a whole lot of things dependent, mostly pitch perception, dependent on the synchronicity of neural firings, not just the spectral contour that they provide. And actually there is a lot happening in terms of the correlation between left and right ear signals. And I mean, to say a signal is probably not a good thing as well, because these are nerve bundles, and the amount of stuff going down a nerve bundle is huge, right? So it's really kind of important to slot in the psychoacoustics as an understanding of, how we don't hear sound, right? So it's much more straightforward, and you can claim that I see things, right? I see that there is a green pen on this desk. But to say that I hear the sound of the projector is a slightly trickier claim, I would consider. True. Okay, so you're seeing here the intermodulation components, and that's actually the biggie for today, that you kind of slot this into your understanding of things. There is always intermodulation components, and that they depend on the nonlinearity, right? So that's why I was saying, if I push two sine waves through a single speaker, they go through a single nonlinear system, and they are prone to give us such components, intermodulation components. If I play them through two separate loudspeakers, then each loudspeaker will, sprinkle harmonics on top, but actually they won't interfere like that. Okay? So actually that's probably, maybe I should just change that for the second experiment. I don't know how long you guys will have the stamina for. I'm off. I don't know if you can tell by the way I'm speaking. But in any case, that's quite important, that if the two sine waves go through the same nonlinearity, they will intermodulate. If they go through a nonlinearity separately, they will not intermodulate. Okay? So actually, interesting thing is that if I saturate two sine waves, I will get intermodulation components. But if I saturate each sine wave separately and then mix them, then I will not get intermodulation components, right? Because they didn't go together through the same nonlinearity. That's the funny thing. And that's something that you can experimentally prove quite easily, actually. Yes?
So you mean say that like the intermodulation is only occurring when there's some other form of distortion there or something?
There has to be a nonlinear distortion, yes.
Yeah. Right, okay.
Yeah. So
when you turn the gain up on there, that was because it was actually starting to like...
Exactly. Yeah. I'm getting into the nonlinear region. It's a crappy little speaker, and it starts to distort. And I wouldn't see intermodulation with two sine waves. Now, the interesting practical thing here is, there's probably one or two guitar players among you already anyway, is that, the guitar pickups, coils, and such, they are heavily nonlinear, right? And they will give you intermodulation components. Now, the point is that is the timbre of it, right? So it's quite important to kind of separate that, you know, kind of, I mean, obviously you guys are not from, you know, the 20s when, but even, you know, I don't know when was this. This was probably 15 years ago. I presented my subharmonic distortion algorithm at a conference, and I got the question, okay, so how do you get rid of it? And I'm like, no, I want it. I want the subs, right? So we are kind of this generation who does understand that distortion is one of the tools. But actually, you know, already 15 years ago, most of the engineers wouldn't even think of it. It's like, oh, if there is a distortion in the paper title, it means they're trying to get rid of it, right? So the times have changed. Okay, so the final real big interesting chapter thingy here is the odd and the even harmonic story. Okay? So the case is, you've probably heard about this odd even harmonics. Anyone wanna, yeah? Where did you hear it at least? Someone must have mentioned it, probably sound synthesis lecture some point, right? So you might know that certain geometrical waveforms have all the harmonics, and certain geometrical waveforms have only odd harmonics. Any idea, clue?
Square wave is only odd harmonic.
Yes, square wave has. The way you can remember it is that point symmetrical waveforms have only odd harmonics. You need an asymmetrical waveform to get even harmonics out of the equation. So the sawtooth wave is the only one which has even harmonics as well. So triangle and square wave don't have even harmonics. Okay, only sawtooth does. Now that's an interesting thing if they introduce it with a bit of interest, I guess. But unfortunately, the story typically stops there. But and I don't know. Again, I haven't been teaching you guys the instrument acoustics either. But it's worth mentioning that if you have a string which is fixed on both ends, you will get all the harmonics, right? So 2 times, 3 times, 4 times, and so forth. If you have a reed, a saxophone reed, which is fixed at only one end, then you will get the first vibration mode looking like this, which kind of makes sense because it's dangling. It's a bit like a ruler, right? The second one is actually this, which also kind of makes sense because that's the way the only next way it can dangle, right? Because it's still going up and down here tremendously. This is the maximum amplitude region, but it's kind of doing it in a higher mode because in the meanwhile it's bending internally once as well. And then if it does 3 times, it looks like this. And if you look, this is the 1/4 of the sine wave, so to speak, right? And this is actually 3 times that, and this is actually 5 times that. So if you have a string, you will get all the harmonics, first, second, third, fourth. If you have a reed, you will get only odd harmonics. This is a matter of physics. Okay, so that's why a clarinet sounds hollow, as they say, right? Because, I mean, only in the ideal case, in the math of it, is it such a clear picture. If it is anything real life, there will be second, fourth, and sixth harmonic, but they will be much lower level. Okay? So that's one domain where you can encounter this distinction. And then the other domain is exactly what we're talking about today, is distortion. So if you have a symmetrical transfer function, and I haven't talked about transfer functions much, if it is a symmetrical transfer function, so this is my saturator, you probably guess that, then I get only odd harmonics. If I have a non-symmetrical transfer function, something like this, then I will get all the rest. Anyone want to guess which device has this type of transfer function? It's a valve or tube, right? But actually, what I can do is if you guys are building distortion algorithms, that went quick. you can actually just make it asymmetrical by any possible means, and as soon as you depart from a symmetrical transfer function, it will start bringing in the even harmonics as well. So the transfer function, and I will spend a minute with this just to hopefully make it clear, or shall I start as a question? So you've seen this type of transfer in a saturator, okay? And you've seen typically this type of transfer for a compressor. So why? And how? And what the hell? So what is the difference between saturator and a compressor? So you see both have two axes. One is, as always, input signal horizontally, output signal vertically. So that's how you can read it. You can say that if the input signal is 0.5, output signal is 0.5. But if the input signal grows to 1.2, then the output signal is keeping it low at 0.9. So there is a linear region, right? And then suddenly we get into the nonlinear region. So that's your saturation. Which device gives you saturation in real world? I mean, computers are in the real world as well, obviously. But tape gives you saturation. If you push an amplifier, it gives you hard clipping. Because it comes to the rail and it just cuts it right there. In order to get any kind of smooth saturator, you need, I mean, one of the things you can do is you can use magnetic tape. Okay, so compressor, on the other hand, well, it's kind of similar, right? Because I have a 0.5 which matches to 0.5. Obviously, this is a mess. It's not exact. And if I have 1.2, it matches to 0.9. So it's a really similar thing. And the magnetic tape does compress, right? So what are we looking at here? What would be the distinction between a saturator and a compressor?
Isn't it just the time domain factor?
Yes, it is exactly that. So what happens is that the saturator actually operates on sample values, and the compressor operates on amplitude estimation. So if this is my signal, right, then the saturator will, you know, saturate or kind of round off all the peaks like that. But the compressor will first estimate the amplitude, which will be this, and then it will try to round things off. Okay? So that's also why you see that the compressor has what we call a unipolar transfer function. It only shows you the plus area, whereas the saturator is a decent bipolar transfer because it also defines what happens to the negative values. You see, if I have an amplitude estimation, there are no negative values, so I don't need to define that at all. Now, the interesting thing is that actually both are nonlinear devices and both will give you harmonics and intermodulation components. Okay? I have asked at one point, I like to hang out with people who are much more clever than I am in this stuff. And I've tried to come to the bottom of, okay, but how can I design a distortion whereby I can control the amount of intermodulation components? Right, that's the interesting thing. And I didn't really get an answer that I could, you know, interpret as clear. But the interesting thing to add here, now that we're talking about these distortions, is that obviously distortion is, in most cases, amplitude dependent. Okay? So if I'm in a linear region, there is none, and then they start coming up. Now, the real interesting thing that we've discovered some time ago, and we've named it harmonic instability of distortion, is that certain distortion algorithms, devices, will have a fairly monotonous increase in the harmonics. So as the amplitude goes up, so this is the input amplitude, and this is the harmonics amplitude. So as the input amplitude goes up, first we are in a linear region, and then let's say that this is the second harmonic, and it starts going up after a certain threshold. Then typically what you have is that the higher order harmonics are of a lesser level, and you get a little thing like this. So this is typically what you would expect. But if you actually start measuring around these things, it transpires that most of them do something like this. And then the second one does something like this, and then the third one is suddenly a bit more flat. So actually, as you increase the amplitude of a sine wave at the input, if you do this monotonously, it is not given that the amplitude of the harmonics will increase monotonously. Okay? So it's interesting to consider, because you see, and then we can come a bit to the Volterra series as well. Because you see, the interesting thing is that if I look at this distortion graph here, what's missing? Where is my distortion graph here? Hello. Okay, let's get rid of these. Get rid of everything. Hello, everything. Bloody hell, there's a lot of things here. Okay, can I see it now? So this distortion graph, what's missing? So it's really lovely that I think see things across the spectrum per a harmonic. Obviously the intermodulation is missing. But there is another thing missing. There is missing the actual variable amplitude, because the distortions are very dependent on the amplitude, and this is just a fixed amplitude thing. Okay, so what I can do then is I can try to make another one. So let's do a really loud one. It's probably going to clip anyway. Well, I really push it to the limit. But anyway, we don't have too much time. But the point is that if I do a plot of distortion with loud settings, it will give me, you see it here already. This one is much louder. You get these really nasty loud harmonics coming up. And if I do it at a low level, they just won't be there as loud. Okay? So, you know, even if this signal, this graph looks very informative, bear in mind that this is at a single amplitude level. And the main thing about distortion components is that they're dependent on the amplitude level. And this is where the Volterra series comes in, because the Volterra series actually contains such graphs for all the amplitudes. Okay, so it kind of becomes the three-dimensional distortion plot. Okay, and that's actually the way you can, you know, come close to analyzing what a device actually does. And you will have models of devices built using this technique, right? Because if you sort all of that out, if you know that at every amplitude level, for every frequency, what are the levels of the harmonics, then you have a really good description of what the system does. Okay, and that's your Volterra series. I mean, I'm not even aware, I don't think, how are you coding it? You said you're trying to code it?
Well, it's just, I don't think I'm actually going to code it. It's just a prototype on paper at the moment. And then I'm going to try implement it. But,
it's tricky. Yeah, I'm not aware of it being in part of Max MSP, not even Super Collider, which I would expect. But you know, if you take something like MATLAB, if you take something like Python, it's in there. You know, so if you're kind of code savvy, you might be able to get to a Volterra series in that way. Cool. Any questions? Did we discuss all of the interesting bits about distortion, nonlinearity, transfer function, odd even harmonics, intermodulation components? I mean, part of the story is that we have intermittent distortions as well. Technically, they call them distortions. You know, we are music techs, so we typically don't. So we are actually talking about the arising of new spectral components. So the message is that every nonlinear process will induce harmonics, right? So this means that the compressor must distort. Okay? I mean, even though it's smoothed out and all the rest of it, it doesn't distort as much as the saturator does. But excuse me?
You guys use the piano?
No, but we have a class.
I'm sorry.
So you see, every compressor must distort. Every nonlinearity must distort. That's a thing to take away on a surface level. That so actually, every dynamics processor is a distortion engine, and every distortion is also affecting the dynamics. So you kind of, if you dig it, I mean, you can come up with examples where it's not obvious or negligible, but these terms are interrelated. A bit like time and frequency as well, right? So in most cases, well, they're just separate terms, and we are happy with that. But actually, if you dig into the matter, you realize that, okay, well, there's some necessary interdependence of these terms here as well. All right, that's that then. So just a brief introduction. What I have for you guys in terms of the exercise is assess, this is the previous one, assess the distortion characteristic of some gear or other. Again, same like that week, you can get it from the text. So first thing is pick 5 equally spaced amplitude levels. Okay, so that's this thing about realizing, measuring, seeing that at different input levels you get different amounts of harmonic distortion. Okay. Now assess if there is a noticeable difference in even and odd harmonic levels. Now you should already be able to predict whether there will be or will not be. Obviously I don't think we have any tube amplifiers to test, but they would likely give you more even harmonics. In fact, I didn't really pay attention to that here, because here I do have the second harmonic, and then I have the third harmonic, right? So actually the second harmonic is way above the third. Am I saying this right? Let me just look at the second and the third. So real life situation, you know, even though I don't assume that there is a asymmetry in the transfer, there is second harmonic just there. Here's the third harmonic. But you see that actually what is likely to be the case is that the even harmonics have a similar shape. In a way, the anomalies, for example, this peak aligns, this kind of looks a bit like that, that peak aligns. Whereas if I have the third harmonic here, I have this thing here which doesn't really match to anything in the odd harmonics, but it might have something that matches to the fifth. So you see, they kind of behave together. Oh, you hardly see that. But even if I, I cannot say, well, there is no even order harmonics there, but I do see that there is similarity in how even harmonics go up and down and how odd harmonics go up and down. Hint, probably not. But, nevertheless assess it. And then it says pick 3 equally spaced frequencies, which is a bit of a, let's see, you guys deserve a BSc in music tech. If I ask you to give me 3 equally spaced frequencies between 50 Hertz and 15K, can you do it? Huh? I'll go over this math. This is one of those things that I think, I don't know how about you guys, but I've obviously studied this at some point as well. And I can clearly remember the moment when I realized, oh, that's how you can divide a spectral range in 3 frequencies, and it made me very happy. So I'll try to transmit that emotion in a second. So this kind of equal spacing in frequency. And then what am I saying is play 2 sine waves that would produce a first order intermodulation component at those frequencies, okay? So I'm obviously pushing it here. So first of all, this bit of math. So the interesting thing is, you guys understand that in frequency, I think I've said some things about this, equal distances have to do with equal multipliers, right? And not equal adders. So if I multiply by 2 each time, then these are octave distances in frequency, okay? This is frequency, right? So the task there is to actually find the multiplier that goes between 2 values in this fashion, okay? So shall we try this example? What I said is let's try to find between 50 Hertz and 15K. And we wanted 3 frequencies in between. Is that how I specified it? Yeah. Well, actually, I say pick 3 equally spaced frequencies. So actually, this is a frequency and this is a frequency as well, and they will be equally spaced. Great. But let me pick 4 equally spaced frequencies, okay, whereby the 2 extreme ones are specified. So I'm looking for 2 points between these frequencies which are equally spaced. So how do I do this? Well, the thing is that this multiplier, so I understand that there has to be one number that takes me from A to B to C to D. I will call this number X. Which means that from A, B, C to D, I get 3 X's, but that is X to the power of 3. So the math goes A times X to the power of 3 is D. Right? And this gives me that X to the power of 3 is D over A. And this gives me that the X is the 3rd root, or the cubic root, I believe it is said, of D over A. So actually that's this thing. In fact, one of the other things that is worth remembering is what is the multiplier of a semitone, right? So 2 is a multiplier of the octave. The multiplier of a semitone is the 12th root of 2. Because what I'm saying is that I'm going from a frequency to its octave, which is a multiplier 2, but I need a number which multiplied by itself 12 times gives me number 2. And this is something like 1.06 if I remember right. So if I go 1.86 times 1.86 times 1.86 times 1, so I'm doing this, I'm stepping with multiplication steps. If I do 12 steps, the multiplier will be 2, which is an octave. So actually I can divide an octave in any amount of steps by taking that root. So that's similar to this, right? So I'm looking at 3 steps, and I'm not looking at octave, I'm looking at a different ratio, which is D over A, but it's the same kind of thing. Okay, so that's your equal distance in frequency. Shall we do this example? You guys care?
Yeah, come back.
Yeah, let's do it. Excellent. I'm really happy that you say that because it makes me feel valuable. Haha. Okay, so what did we say? We said we had 15K, so that's 15,000 hertz. Supercollider is my calculator anyway. So 15,000, I said 15K. And we divide by 50, right? So that's this ratio D over A, which comes to be 300. Okay? So actually, what I'm doing then is I'm looking to get the multipliers 300 into 3 smaller multipliers, so to speak.
So would you cube root that then?
Exactly. So I take actually this ratio, and I take the power of 1 over 3. Right? So the cubic root is to the power of 1 over 3. Square root is to the power of 1 over 2, right? So this then gives me a number which is 6.69. And, well, now I will call it the x, right? So if this is the x, now I can test my hypothesis that if I take 50 hertz times x, I get 334. If I do that times x, I get 2240, and do that times x, hooray! There's the 15,000. So you see, actually, it is rather counterintuitive set of numbers, right? If you just look at these numbers, I say, okay, I have the following frequencies: 50 hertz, 334 hertz, 2002, and 15K. Well, you'd say, well, there's quite a lot of bass in there, isn't it? But actually, these are equally spaced frequencies right there. Okay? And then obviously in the task, what I'm saying is that I want you to make it so that the first order intermodulation component is that frequency. Right? So this means that you need two sine waves of which the sum or the difference will be that number. Great. Was that a bit confusing? Because you see, what happens is that if I'm producing this intermodulation frequency test, I'm using two sine waves, but actually the question may be open as to at which frequency am I identifying it, right? So if I take a sine wave of 100 hertz, right, and I take a sine wave of 800 hertz, okay, I will get an intermodulation component at 700. But actually, I can also get an intermodulation component at 700 if I take 300 and 400 hertz. Right? So that was part of this tricky task, is that you make it such that the equally spaced frequencies are the frequencies of the intermodulation component that you're looking at. And that then becomes a really interesting one. Do you expect it to be the same level independent of how you create it? Probably not. But never mind. We're having some fun. All right? Cool. So I guess that's that. Grab the gear and I'll be around to give you a hand with these things in a minute. Obviously upload this as well.